Now we are, hold on. It's going live.
It's like waiting for my wife to get ready to go out.
Yeah, I hear that.
Yeah, it's happening. It's happening.
There you go. All right.
You didn't get that bit on video, I hope.
I think so. Hey, everybody. This is Keith. Thanks, Keith, for coming and doing this. It's pretty early in the morning for him. So thanks, Keith.
Thanks, Tony. All right. So this presentation is not the first time I've given this presentation. I gave this at the Australian Online Mini back in April. And there is actually a video of it online, but I thought I would give it again, mainly because it's actually good to do some interactivity. And so I would encourage people to unmute and ask questions rather than sit silent and confused. This is a very technical presentation. I understand if people are going to drop off because it gets very technical for them. But what I will assure you is that through this process, you will definitely come away understanding a little bit more about how your lights work and where issues arise. The work that went behind this presentation was based on a presentation I actually did last year, where I did more of a live demo at our local mini of 2811 sequence signaling, and we threw the oscilloscope onto some wires and understood what signals look like and how various variables started to change things. And earlier this year, I went back and redid that stuff, but in a much more systematic way. And I also spent some time with Bill Porter and John Spiker, talking through some of the results and some of the presentation. In fact, some of the better parts of the presentation are as a result of some of those conversations. So thank you, Bill, and thank you, John. So let's get in it. I'm going to spend some time basically going through and helping you understand why your lights flicker and why it may not be the reason that you think that they flicker, and hopefully give you some ideas as to how you might fix it. I can't promise it'll help in every situation, but I think it'll help in more than you'd think. There's a lot of accepted knowledge out there. Lots of people with, rules of thumb about how things work and why things work the way they do. And that's fine. But I always wanted to understand, just how much of this was true. How does this really work? And where does it really go wrong? And so that's what we're going to spend some time on. So some of the things we're going to go over, we're going to go over wire and its effect on voltage. We're going to look at what the 2811 signal actually looks like and what sort of degradation we get over different types of wiring. We're going to connect it over a number of different pieces of wire. We're going to look at how it varies based on voltage of your pixels. So we are going to actually answer the question of what's the difference between 12 and 5 volt pixels when it comes to things like this. We're going to spend a bit of time looking at things like F amps and null pixels and what happens and how they work and what sort of difference they make. We're going to look at a pixel as a null buffer and talk to how effective that is or isn't. We'll also take a quick look at things like DMX signals and the differential signals that are used between controllers and their remote boards and what those sorts of things. And then we'll also take a look at some termination resistors and stuff like that. So it will get pretty technical through the presentation. What we're going to do is we're going to test this over a number of different types of wire, and hopefully one of these wire types is somewhat similar to the types of wire that you use when you're putting your props together. We're going to work with some alarm wire. This is incredibly thin wire. It's a 4-core wire that's a AA battery there. It's 26 AWG for you guys, or at least that's my best approximation of 0.14 millimeters squared. Typically when I run this, I would run 1 positive, 2 ground, and 1 with data. So I always double up the grounds, and that's generally good practice, and you'll see why soon. I then did it over a solid core Cat5 cable. So we'll run a bunch of tests with that as well. We'll then go to a data cable. So this is a shielded cable, 4-core, it's stranded, it is copper, well, it's actually just aluminium wire. It does have this ground, unshielded ground wire, which I don't generally use. I generally connect the two whites together as the ground. The blue is the positive, and the orange is typically the data. We'll then go to speaker wire. So this is a 2-core 18 AWG wire. I obviously have to run a third wire of the same type to provide the data wire as well. So this one's a bit messy to put together. But this is the most common wire I would use for power injection in my show. And so I did want to test with it. And then finally, this is a 17 AWG light duty extension cord. It is copper, it's stranded, and I wanted to run tests over that as well. All of them have been run over 20 meters or 66 feet of wire. So all of the tests have got a long run of wire, and we're doing the test generally at the end of that wire to understand how the signal has changed over the course of that wire. So let's talk about a voltage drop, right? All wire has resistance. I know people plug wire in and you kind of just assume that whatever voltage you put in at the beginning, you get out at the end. And, you know, at times that's true. If you just throw a multimeter at the end of a 20 meter piece of wire, your voltage is not going to look like it's changed a great deal. And a lot of that's due to this second point, which is Ohm's law, which is that the voltage drop is actually a factor of the current times the resistance. And the resistance is really low. And when you're just doing a straight voltage measure, the current draw is almost zero. And so consequently, you're not going to see a great deal of resistance out of the wire. But there is actually resistance there. And the more current that you draw, the more resistance there is, or the more voltage drop that you will see in that wire. And so consequently, you will notice that you will see signaling behavior and pixel behavior that varies depending on the brightness of the pixels or the number of pixels that you turn on. And that is largely as a side effect of this formula here. When you turn your pixels on all white, the voltage drop is much greater. And as you'll see, the voltage rise is a lot greater as well. And we'll talk about that. That's also why dimming your pixels down will reduce the current draw. It doesn't change the voltage or the resistance, but it does reduce the current draw, and therefore it will change the voltage drop. And that's why lowering the brightness of your pixels will often lead to less issues with flickering. It's also why there's actually differences between the data wire and the power wire on your pixels, because when you're running your lights, there is still, even when you're running your lights at full brightness, there's a lot of current draw that's going over the positive wire and returning back down the ground wire. But the data wire still has almost no current draw at all. And so consequently, you see the data signal changing differently to the power signal or the power supply to the pixels. And we'll see in this presentation how that affects things. So yeah, so consequently the voltage drop, if you get zero current draw but lots of resistance, you still get zero voltage drop across the wire. So to test properly, you have to add load. And in all of these tests, I've put a load. It's not a huge load. And so consequently, your results may not be anywhere near as favorable as even mine are, because you'll probably be running a lot more pixels off the back end of this wire than I was in this test. The test setup, I used both 5-volt and 12-volt pixels. Most of my tests were done with LED nodes. These are the nodes where there are actually 3 LEDs, but only a single 2811 chip. Some of my tests I did run with actual pixel nodes where it's 1 LED per 2811 chip. We'll talk about those when they come up. And the 5-volt tests were typically 38 pixels, and again, typically at all white. I would typically have my controller connected up to a long test wire, and then the test point is where I would typically take my samples. and then I would have a bunch of pixels hanging off the back end of that. So I was testing what the signal was looking like going into the first pixel generally. And the reason for that is that the signal generally gets refreshed once it gets past the first signal. So testing at the end of the pixels or even after the first pixel doesn't really get you to understand what the signal looks like as it goes into the first pixel. And as you'll see in the results, the first pixel is often where the problem is. So this test here, and I won't claim these are enormously accurate. I definitely struggle to get good resistance measures this low on the wire. But using those various pieces of wire, you can see the sorts of resistance. So starting with the power, which is by far the heaviest duty wire, you can see that when I turned all the lights on, so this was all the lights on, the power started at 5 volts at the power supply, but by the time it got through that 20 feet, or sorry, 66 feet of wire, it was down to 3.5 volts with 5 volts, and 12 volts it was down to 10.56, and the resistance of the wire was about 0.7 ohms. So not very much at all, but still there's a resistance there. As I moved to the speaker wire, the voltage dropped slightly on both. The resistance was marginally higher, but only marginally. It's a reasonably heavy speaker wire. The Cat5e, the resistance basically doubles to 1.9. And you can see that the voltage is going down progressively. Well, by the time you get to the data cable, the resistance is up to 2.3 ohms, and now the pixels in the 5 volt pixels are starting to glow red, which means typically that the blue, and in this, by the time it's getting to pink, it's starting to lose the green as well. And we'll talk about why that happens. And then with the alarm cable, which is slightly higher again at 3 ohms, the 5 volt LEDs were pink and red and steadily on, and the 12 volt LEDs were down to 9.4 volts, and they were glitching at this point. So not looking good. And by glitching, I mean, I think they were flashing on and off from memory. So you can see how the various types of wire are delivering different electrical properties in delivering the signal. So let's talk about what a 2811 signal looks like. So a 2811 signal is, it's a data signal. It's a 5 volt data signal. Even if you're running 12 volt pixels, the data wire is still at 5 volts. This is why, and this is true across all types of pixels. It's why if you can run pretty much any voltage pixels off a controller as long as you only connect up the data and the ground wire and provide the power supply directly to the pixels. They don't really care because the data signal is still always 5 volts. It's very low current, so consequently you don't see a great deal of voltage drop, and thus you're not seeing a lot of issues for that reason. The signal runs at about 800 kilohertz. That's 800,000 cycles per second. That's actually the end-to-end. The actual signal changes occur at roughly twice that frequency. The high transition voltage and the low transition voltage, these things are important. It's important to understand that when the pixel is detecting the signal, it is detecting whether the signal is high or whether the signal is low by looking at its ratio to VDD. Now, what does that mean? Well, that means that if the voltage hitting the pixel is 5 volts, then VDD is 5 volts, and 0.7 of 5 volts is 3.5 volts. But as you saw in the previous slide, well, if the power is actually 3.5 volts when it gets to the pixel, then the high transition is 0.7 times 3.5 volts, which is obviously lower. And this becomes really, really important because when you've got 5 volt pixels, you'll notice how the 5 volt pixels didn't glitch, but the 12 volt pixels did. And the reason for that is as the voltage goes down as it lands on the first pixel, the signaling voltage, the voltage that the pixel needs to determine whether something is high or low, also decreases proportional to this voltage drop. Whereas with a 12 volt pixel, that doesn't work quite the same. And so consequently, 12-volt pixels are infinitely more likely to glitch than 5-volt pixels are. 5-volt pixels will suffer color change, color degradation, etc., but they generally will not glitch. Now, the signal itself is represented by two signals. A 0 is basically the signal goes high for a period of 0.25 microseconds, and then it drops to low for 1 microsecond. And a high goes high at the beginning for 150 nanoseconds, sorry, for 6 microseconds, and then it drops back down for 6.5 microseconds. And effectively, the way the pixel is actually doing this is it detects the rising edge. It then has a timer, which is probably something like a capacitor or something, and it waits a certain period of time. And at that certain period of time, it reads the signal, and whether it's low or high at that point when it reads the signal, it's either reading a 1 or a 0. So this becomes really important, because when the signal is a nice clean shape like this, you can see how these are nice and easily read. But as you'll see in a minute, these signals are not this shape. These signals will be rounded off. They'll have deformations on them, etc. And so if this signal in a 1 for some reason starts to degrade early, then this may not be read as a 1. This may be read as a 0. If this peak here doesn't get to this transition voltage, then it won't even see the signal, and it will just assume that there's no signal at all. So you do get all these sorts of problems. The other problem that you'll sometimes see with the 1s, and you'll see this in a minute, is that the signal won't actually rise up very quickly, and consequently the time that it's high here is not as long as it should be, and so it mistakenly gets read as a 0, and that will clearly lead to flickering as well. At the end of the string, the way in which 2811 works is it pumps the data out down the wire. And the way in which basically the first pixel reads the first 24 bits of data and then passes everything else on. And the way it knows that it should read the data is that it experiences a period when the signal goes low for at least 50 microseconds. And that's how the first pixel knows that we've reset and the signal is now being sent to the first pixel in the string, not some other pixel further down the string. So the reset becomes kind of important. And so you can do some math here with all of these numbers and work out how many pixels you can theoretically run. So if 1 bit takes 1.25 microseconds, then that works out as roughly 800,000 bits per second that I can send down the wire. And if I need 3 bytes or 24 bits to actually represent a pixel, then it's obviously going to take about 30 microseconds, which means I can actually drive about 33,000 pixels per second down a piece of wire. But of course, we don't run frame rates of once per second. We run 20 frames a second or 40 frames a second. And so if you do the math and you take into account this reset time, etc., the theoretical maximum at 20 frames a second is about 1600. And the theoretical maximum at 40 frames a second is about 831 pixels. But of course, none of our controllers run that many pixels per second. And the reason they don't do that is because there are overheads associated with preparing the data to send out. That overhead varies based on the speed of the controller's processor. It varies based on the degree to which the controller is trying to synchronize the signals and not do frame tearing and things like that. So, you know, you're not going to get this many frames per second. And if you do get really large numbers of pixels per frame, it invariably means that there's some compromises that have been made or some risks taken that you might get some frame tearing that you probably won't notice, but that's why it is. Any questions on that? Is that all pretty straightforward? I'm boring everyone to tears.
Question in the chat there.
Well, real quick, when you say controller, are you referring to like per port or the whole controller itself?
No, I'm talking about per port. It really only matters per port because the pixels only see the data that's going out each port. So these numbers here are per port. And this is why, you know, most controllers typically top out at about 680, 700 pixels for 40 frames a second. And for 20 frames a second, they're topping out at between 1024 and 1400 pixels. And that's why they've chosen these numbers. They've chosen these numbers because that's all they can actually clock out in that amount of time. Okay. Let's go on. So what does it actually look like? Well, these things are produced with a piece of software from a company called Soleil, who make these digital signal analyzers, which are these amazing tiny little boxes that are, you know, just a couple of inches square, which capture digital signals. And this is what this is a 2811 signal captured from, I think this was my Falcon F16, and you can see that it's, you know, it's 800 kilohertz. You can see the signal timings. Dave doesn't use, strictly speaking, the standards. Dave has found that if you run the high a little bit long, you generally get better compatibility across a broader range of pixels. And so he does run slight, you know, he runs 7.75 microseconds, which is right at the end of the threshold here. This is the error factor on what the signal's allowed to be. And so Dave runs his signals right at the top end of that error factor to provide the best experience and the most compatibility. You can see also that the controller is sending, this is a blob of data. There's a whole bunch of pixels that are being sent here. And then there's this long quiet period before it sends the next frame. Now I was only running my 38 pixels or so. So this is actually quite a large amount of downtime that's going on here. So that's what it looks like digitally. Of course, that's not what it actually looks like. This is quite a pure signal. This is actually a pretty good signal taken at the end of the string. So this is the signal that's being cleaned up and is being passed from pixel to pixel. But even though this is a pretty good signal, you'll notice it is nowhere near as clean as this signal here, right? This is a digital signal, which means it's taken a sample of this signal and squared it up and is representing it as a very square signal. The other thing that you'll notice here is that this is a 0 and this is a 1. You can notice the 0 is a bit shorter, the 1's a bit longer. But the overall period of the signal is pretty much the same. You'll also notice there's some AC effects in here. There's a bit of a ripple voltage inside this as well. The actual voltage of this signal is roughly 5 volts. This is 1 volt per segment, and it's about 5 segments high. It's a little bit under 5 volts, but it's pretty good. That's a pretty clean signal. But when you zoom in, you can see that it's not perfect. There is a rise time to the signal, and there is a fall time to the signal. This is a pretty clean signal, right? You'll see in a minute it's not typically this good. 0.7. So remember from this slide back here, we said that it's going to take the high transition voltage as 0.7 of VDD. Well, let's look what that means. Well, 0.7 of VDD. So VDD is typically, in this case, because I think these were 5 volt pixels, the top voltage here is typically the same. So 0.7 of VDD is going to be roughly where this arrow is. So that's when it's going to read it as a 1. It doesn't read it as a rising edge back here. It doesn't read it as a rising edge here when it reaches its peak. It reads the rising edge at this point here. And that's when the clock starts before it starts to sample the signal. The fall point is actually here. So the fall point is 0.7 down. So it's not when it starts to fall, it's actually when it started to fall a fair way. And that's when it's going to read the 0. And you'll notice that the signal has now been shifted. So the controller thought it set it high here. The pixels thought it was high here. The controller thought it set it low here, but the actual low signal was here. So that's how it's interpreted by the pixel. So let's have a look at the various types of wire and let's see what happens when I don't do the test point at the end of the pixels, but I do the test point before the first pixel. It ain't great. It's definitely nowhere near as clean as that prior signal that you were seeing. And it's quite different, as you can see, between 5 volts and 12 volts. You'll notice here that this is somewhat disturbing how the 5-volt signal is. So the signal starts to rise, it reaches a certain point, it plateaus, and then it only spikes at the end. This is going to make this thing incredibly sensitive to VDD. Because if VDD is such that 0.7 is up here, then it's not actually going to read the rising edge until right at the end of the signal, which means, you know, even in the case of a 1, although in the case of a 1 here, you can see that on the 12 volts, there's no 1s here. These are all 0s. You can see here with the 1, it's probably going to read the 1 here. So the time between here and probably roughly here had better be long enough for this to be read as a 1, or this is going to be erroneously read as a 0. There's a risk here if this voltage falls at all that this won't be read at anything at all as well, particularly if the voltage starts to degrade. So yeah, you end up with quite a different shaped signal or timing of signal. There's your 1 and there's your 0 on those signals. So you can see that there's a certain amount of risk across the wire, and this is on the wire with the least resistance. It's going to change as we move. So this is the speaker wire. Now the speaker wire, interestingly, produces a much better signal. I never truly got to why that was. It's possible because whereas the wires are all bundled tightly together with the speaker wire, the third wire was sort of just loosely cable tied to the other dual core wire. And so it's possible that the capacitance between the wire was different and that changed the way the signal shape was. But this one here actually turned out to be pretty good. The 0's pretty wide and the 1's even wider. This is Cat5e, similar signal shapes. Not enormously different. Here, the 0's being detected a little bit better, so the signaling properties here do seem to be slightly better. This is the data cable. And finally, and there's the signal there. So again, quite late. The 1's not too bad. And this is the alarm wire. The alarm wire is extremely late and the 1's not too bad. So why this shape? Well, what causes the signal shape to change from what goes in on the input side of the wire to the output side of the wire? Well, one of the key things is capacitance. Capacitance is where when you have two parallel wires, there is a certain amount of charge that gets stored between the wires. And what that means is that when you try to change the voltage between the two wires very quickly, that charge is either built up between the two wires, or when you turn it off, it's released from between the two wires. And that has a tendency to round the signals off. And so the rounding that you see on the front end of the signal and the rounding that you see on the back end of the signal is typically a capacitance effect. And the longer the wire that you run, the closer the wires are together, the more capacitance that you're going to get. So yeah, it's a logical capacitor there. So you definitely don't want to be trying to fix your signals by adding capacitance. That ain't going to help. The other thing that you can get is inductance across the wires as well, and that can lead to things like, or impedance mismatches, which can lead to signal reflection. We'll come back to that. So what does a signal look like when it's flickering? So here's a signal that was flickering. Right, I was running the best wire, which means I was running the power wire, the one with the least amount of resistance, and these 12-volt pixels were flickering. And the reason is that the signal was varying over time. These are 2 volts per division. And you can see that there is a significant amount of voltage variation between the zeros and the ones here. In fact, so much so that these zeros were probably not being read at all, and the ones were probably being read, which means this signal did not comply with the specifications at all. And so when the signal is 0, the peak-to-peak voltage here is 3.12 volts, which means you're seeing this significant voltage change. Where it's 1, it goes to 0.8 volts, which is 3.76 volts peak-to-peak, right? So this 3.12 volts, particularly if it's receiving 5 volts. And the thing about 12-volt pixels is the VDD with 12-volt pixels is generally going to be closer to 5 volts. With 5-volt pixels, the VDD drops as the voltage drops and down the line. Whereas with 12-volt pixels, because they're either regulated or they're using a resistive dropper, tend to keep the voltage much higher. And so consequently, as the signal voltage changes, the chances that they're going to hit that threshold of 0.7 times VDD becomes a lot worse. And so you get these signals which get into really unreliable territory. And so you'll get 2 types of problems here. You'll either get things where the lights lock on white, the lights flicker between, say, white and black, or more commonly, you'll start to get random colors. And that's typically because the signal here is being read where, some ones are being seen, the zeros are generally not being seen. And so you get these signals which are quite screwed up, and your lights will flicker all sorts of random colors. And I've seen both with my pixels. This is the money slide. This is all Bill Porter. He provided the idea behind this slide. If you walk away from nothing else in this presentation, this is the slide that you need to understand, because this is going to explain why your pixels have problems and why it's not necessarily what you think it is. So what I've done here is I've taken a voltage, and this is done with 12-volt pixels. And I've done it with the power wire, so the best wire with the least amount of resistance. And when I measure the voltage at the controller, my ground is 0, my data signal is at 5 volts, and my 12-volt supply is at about 11.51, and there's obviously an error factor. When I run these pixels on a really, really dim red, really just the lightest of reds, just so that I can see that there is actually a signal going through the wire, things start to change. Now, the first thing I want to highlight here is I am showing that the voltage or the ground wire is no longer 0. It's at 0.3 volts. And you're going to say, well, hang on a second, I thought ground was ground. Well, ground is ground, but it's not necessarily the same ground along the whole length of the wire. And this is something that you have to start realizing. As much as you will see the voltage drop over the length of the wire, you will also see the ground equally come up from ground. And what actually happens is the voltage range narrows. So part of it is the positive dropping, but part of it is the ground coming up. And the reason for that is the current flows both out across the positive wire, or actually technically out along the negative wire, and then back in the positive wire. And so there's actually resistance and consequently voltage drop on both sides. And this is what people don't realize. And because the voltage drop is different on the positive wire than it is on the data wire, you're going to find that this narrowing of the voltages is quite different. And this is where your flickering comes from. So how do I know this is 0.3 volts? Well, basically, I put my my voltmeter on the controller ground, and I put it on the ground wire at the first pixel, and I measured the voltage difference, and that was the 0.3 volts. And there was a slight drop in the signaling voltage and a slight, well, in this case, increase, but you can read that as effectively the same thing in terms of the positive. When I turn the wire on all white, things start to change dramatically. I start to see a significantly greater drop in the voltage. And notice that if you put a voltmeter at the pixel here, of course, you would be reading 10.9 volts minus 1.8 volts. Sorry, yes. And that would be the voltage that you'd be reading, which is going to be what? 9.5-ish volts, which would look fine. You'd look at that and say, that's plenty of voltage. My pixels should be great. But what you'll notice is that the ground has risen up by 1.28 volts. And so when I look at the difference between the data voltage, which is 4.6 volts, and the ground voltage, which is 1.8, this is what? 3.3 volts. So if the pixel, the chip is receiving 5 volts, this is now 3.6 volts. That is, 3.3 volts, sorry. That is disturbingly below the threshold voltage for detecting the rising edge on the 2811 signal. So even though I've got plenty of voltage here on the pixel, this pixel is likely to flicker and not read the signal correctly. Okay, so this is why if you had an extra piece of wire that you wanted to add, you would not want to add it to the positive, because changing this voltage up here is going to make very little difference. In fact, it could make the flickering worse. What you need to do is add it to the ground, because when you add it to the ground wire, you're going to reduce this voltage drop. The more wire that you run here, the least resistance you have. The least resistance you have, the less this voltage rises up towards the data voltage and starts to cause signaling and flickering issues. Okay. The final thing I wanted to show is, well, what happens if you throw an F-amp in? And by F-amp, you could also use, any of the null buffers, etc. Well, interestingly, you'll notice that the voltages change, but it's not the ground voltage that changes. It stays at 1.28 volts. But what happens is the signal voltage suddenly leaps up to 6.29 volts. Now, this 6.29 volts is 6.29 volts when compared to the controller ground. It's actually 5 volts compared to the ground at the point where the F-amp was. So what it's doing is it's restoring the gap in the voltage between the signal voltage and the ground at that point. And that is why something like a null buffer or an F-amp makes a difference to your signaling. Now, there is another difference to the way the F-amp works. The F-amp doesn't use the same characteristics to determine that transition between a 0 and a 1. Where the pixel is waiting for the voltage to get to 0.7, the F-amp or the null buffers have a tendency to trigger at a much lower voltage, which means they tend to square up and widen the signal a little bit more and reduce the loss due to that capacitance effects on the wire. And that's why if you introduce these things into the wire, you can suddenly get that flickering going away. Questions? This one matters, guys. If you don't understand this slide, the rest of the presentation ain't going to help you.
Okay, Keith, question. So I'm just trying to understand what you're presenting here. So basically what you're saying is that the problem isn't so much it's a voltage loss. It's being able to distinguish the data between the positive and the ground, right? Because the whole point is on that curve.
Sorry.
Because that curve, you want to be able to distinguish a 1 from a 0. And if it gets too close, and we're seeing it get too close between ground and data, then it has a hard time distinguishing. And what the F-amp is doing is it's getting the data back into the middle. It's not actually fixing your voltage loss.
That's right. It's not doing anything to your voltage loss. It's restoring the data signal to a better signal, and it's slightly widening the signal back out again to compensate for those losses due to capacitance. Okay, so you're ending up with a much sharper signal. And I'm going to show you some pictures in a minute, which will show you actually the signals and what an F-amp does, and I'll show you a before and an after, etc., so you can see that. Right, but the ground is your problem. It's a big problem, as you can see. And it's a bigger problem with 12 volt pixels. And again, we'll cover more of that in a minute.
Keith, I have a question.
Yeah.
if you added, as you suggested, more ground wire or a second ground wire, in that case, what would we expect the white voltage to be and the F-amp voltage to be, the ground voltage to be if you added a second ground wire?
So let's imagine for a moment that we doubled the ground wire. Okay, so doubling the ground wire should roughly halve the resistance. And so we would expect this voltage here to be closer to what, 0.65. So this won't change. The 4.6 won't change. This would change. It'd be slightly bigger. And so the signal would be read better at that point. This would then also be 0.65. And this would be 0.65 plus 5. So it would be 5.65. It wouldn't boost it to 6.29. It's really only, it's boosting it relative to the ground by 5 volts. So whatever that was at that point, it's going to do it. So if this was 2 volts here, this would boost this to 7. Assuming that this voltage is higher. Now, this would be very different if this was a 5-volt pixel. Very different.
So when the F-amp is cleaning up the data, what it's doing is it's just centering the data right in between the ground and the positive.
It's not even, no, it's not even centering it. If that's centered, that's coincidence. What it's doing is it's adding 5 volts from this voltage to what, and making that the new signal voltage.
Okay,
right?
so
Because,
it just adds 5 volts regardless of where it is. So
well,
if you put your F-amp in the wrong
it has
place,
the headroom. Assuming it has the headroom. If it doesn't have the headroom, then obviously it won't. But if it has the headroom, it will add the 5 volts.
I have a quick question. With the F-amp taking it to 6.29 in this instance, wouldn't that be too high for the chip to handle anyways?
No, because remember, the chip is seeing this as 0 and this is 5 volts.
Okay.
Right? Remember, I'm measuring these voltages back to the controller, but the pixel doesn't see this 0. The pixel sees whatever's here. So it doesn't care. Right? And this is the thing, you got to imagine this is both this is done over a long distance. But I've done it to give you an illustration of what happens, because what matters is these gaps between these signals and not necessarily the fact that this is the zeros back here and this is 1.28 is not a problem. What matters is the gap between these two lines at that point.
What's the minimum positive you can run on a pixel? I see it 10.9, but what's the minimum before it starts having issues?
So it really varies in a couple of different ways. So take, for example, so if this is true, why do 5-volt pixels never flicker? And they don't. Literally, you can run 5-volt pixels to the point where they're red to they're off and they will never flicker. And the reason they never flicker is because the voltage supply that is going to the 2811 chip falls away. And so the signal, the threshold for detecting the signal also falls away. Remember, the voltage, how big this gap needs to be here is not a constant. It's not always 3.7 volts, which I presented on that earlier slide. If the voltage that's being provided to the chip is not 5 volts, but it's 4 volts, then it's 0.7 times 4 volts, which is what? 2.8 volts. So this would be a fine signal. If I was only providing 4 volts to the pixel at this point, this would be a perfectly clean signal. I might have other issues with color of the pixel not being adequate because you need certain voltages for the actual LEDs to turn on, but the signal would be fine. This is something that is uniquely a problem with 12-volt pixels. Right? And it's uniquely a problem at the first pixel generally in the chain, because that's where this happens. Because once you go through the first pixel in many ways will act like an F-amp. It will boost the voltage coming out of the pixel by 5 volts. Now that does change. That's very true with regulated pixels. With resistive pixels, that's not quite as true. Because with a regulated pixel, the voltage going to the 2811 chip is pretty much always 5 volts until this voltage gets quite low. But with resistive pixels, the voltage going into the 2811 chip actually varies because it's actually proportionate to the input voltage. So once it gets to 10.9, the resistor will drop the voltage to something that's likely under 5 volts. And so you will get less flickering, and I'll talk about this in a little while, but resistive pixels are a little bit less susceptible to flickering than regulated pixels are. But once you get past the first pixel, regulated pixels are much better. We good? Shall we move on? All right. Okay, so there are a couple of ways that the signal can be misinterpreted. The ones can be shortened and shortened to such a degree that by the time it starts to sample the value, it's seeing it as a 0. So the leading edge is seen really late, or the zeros don't ever get to the threshold voltage, and so the entire signal is missed, i.e. the leading edge is never seen. Okay, and that results in, as I said earlier, either random colors, locking on. Typically that's going to happen when they're all white. I used to have this problem with my icicles, my 12-volt icicles. If I ever turned them on full white, they would just lock on white, and after that they would never change. Even though the controller was still working, it couldn't change them, and the reason was there was so much current draw going into those icicles that that there was so much ground rise that it was no longer able to see any signal at all. And so it was just sitting there saying, well, I'm waiting. Someone tell me what to do. I'm stuck on white until someone tells me to do something else. And it could never see the signal, even though the signal was being sent. Flashing is another one that I've seen. And this typically only happens when I had this in a number of my tests where I would set it to turn it on all white. And what it would do is it would alternately turn on all white and then all off. And the reason for that was when it was all off, it would read the signal and it would say, okay, I should all turn on. So it would turn everything on. At the point of turning everything on, the next signal would come in, and this would shorten the ones to the point where they were now being read as zeros. And so it would say, oh, you want me to turn them all off? So it would turn them all off again. And so you'd get this flashing of the pixels going on. And that was a signaling issue, again, due to the rise in this ground. So then the next question I asked particularly was why this shape? Why when you look at the signal, and the one we were testing, this is the Falcon with its default resistance, you get this foot, this little sort of ledge at the back end of the signal. And I was curious as to why was that happening? Because, capacitance explains it being rounded on the way up. Capacitance explains it being rounded on the way down. But why did it have this weird shape? And I had a bit of a chat with a few people. And it turns out that this is largely driven by the resistor that sits on the output of your controller. And so all controllers have a resistor that sits on the data wire as it goes out to the Euro connector that then connects out to your pixels. And depending on the value that's put in place on that, you get a very different signal shape. So what I did was I pulled the resistor network out. The resistor network on the Falcon is 100 ohm, whereas the 2811 data sheet suggests that about a 33 ohm is a more appropriate value. So Dave's gone a bit high on this value. And then what I did was I threw in a resistor tester that I've got, and I put in a bunch of different resistive values, and I took samples of the signals. And you can see that it definitely produces a better signal at 30 ohms. There is a lot less of this foot on the signal. You don't have the same, well, you don't have as much of this sort of stepping going on the way up. And so something between a 30 and a 50 ohm here will generally produce a better value. Now, this is somewhat dependent upon, the wire that you connect and everything else. But one of the things that you could definitely contemplate if you wanted to get more distance out of your Falcon controller is replacing these resistor networks with a 30 or a 50 ohm resistor network, and you would likely get better signal driving. Of course, the other thing that you can do is you can throw the null buffer in, because interestingly, the null buffers all have 33 ohm resistors hanging off the back end of them. And that's why even connecting an F amp to immediately to the output of a Falcon controller may well still clean up your signal. This was something that I found last year in the demo that I did at the Sydney Mini, and I couldn't explain why it was that throwing an F amp at the controller would suddenly clean the signal up significantly at the back end. And this is largely the reason why that's true. And so for about 70 US cents, you can buy these things, and there's about 8 of them sitting across the back of your Falcon, and you can sort of swap them out and get better signal driving. Now, I wouldn't do this if you don't need it, but it's an alternative rather than buying F amps.
Keith, one question on that. Did you happen to run a test where you had no resistor?
No, I did not run a test without a resistor, because I started with the data sheet, and the data sheet, if you go and open up the WS2811 data sheet, it specifically talks about the need to have the 33 ohms. And the reason it's 33 ohms is because it's actually 33 ohms on the other end as well. And matching those resistances is the thing that helps the signal not have reflections.
Okay, thanks.
So yeah, I would not expect it to be better with 0. So how does the type of pixel and the voltage impact the signal? Fundamentally, it's complicated. I did actually put this spreadsheet together, and I can kind of predict when pixels will fail, when they will flicker, when the colors will start to degrade, and so forth. And, through this analysis, it was pretty clear to me that 5-volt pixels will generally not flicker, but colors will become an issue. 12-volt resistive pixels will eventually flicker, but they will generally go a little bit further, and so forth. So let's run those out. So let's sort of boil it down to those sort of simple rules. 5-volt signal reception is pretty much always okay, and you'll get much better distance to the first pixel than you will with 12 volts. I run 5 volts easily at the end of 60-foot cables, and I've never had a signaling issue where the 5-volt signal was not being received. Your bigger problem will be color loss, and the only solution to that is clearly power injection. But you can run your signal as far as you like. 12-volt resistive, you will get longer runs without color loss than 5 volts, absolutely. They will lose color before you will lose color with regulated pixels, so they're not quite as good at driving distance as the regulated pixels are. You will get color flickering if you push them hard enough, and you can improve that by adding an additional ground wire. You will get greater distance to the first pixel than regulated. Regulated pixels will flicker earlier than resistive pixels. And that's just because they provide the voltage to the 2811 chip slightly differently, which means regulated pixels have a tendency to provide 5 volts more reliably to the 2811 pixel. And paradoxically, that actually is a problem rather than a good thing. And obviously the reverse then applies for regulated. You get longer runs without color loss. You will get flickering or locked on white, and you can improve it by adding that ground wire, and you'll get slightly less distance to that first pixel. But you can throw in null pixels, right? And this is the thing, right? You can totally solve this issue by throwing in, F amps and the like liberally wherever you need, either sometimes just before the first pixel, sometimes halfway, depending on the controller that you're driving from. Even putting them at the controller themselves will get you better distance. Okay, let's move on to some other things. I did want to check the various types of null pixels. So I had 3 of them. So I took a 2811 pixel, and I thought, well, what happens if I do one of those? In this case, what I did was I actually put the null pixel immediately after the controller to see how that would work. So I am running the alarm wire, which I think was the worst wire that I had to do this test. I am using a 2811 pixel. There's a Hansen pixel null buffer that's buried under all of that shrink wrap and over enthusiastic Scholastic. That's what it actually looks like before it's been soldered onto. And then there's an F amp as well. So this is a null pixel. Well, sorry. You can see that, this hasn't really made that much difference. These are before and after shots. It doesn't really do that much good. I was a little surprised by that. I was hoping that a pixel would, given that the impedance mismatch would have a better thing. And you do notice that the foot has gone away. So that impedance mismatch has disappeared, but it doesn't drive the signal, and it also doesn't trigger early like an F amp or a null pixel does. And so you don't tend to get the signal elongation and squaring up, but it does get rid of the reflection in the signal. So it is slightly better, but not much better. This is the Hansen null buffer. You can see that this really does drive the signal pretty hard and squares the signal up pretty dramatically. The capacitance effects are still there. Obviously, I'm running this over the speaker wire, and so you are going to get a bit of the capacitance effects there, but it does drive the signal a lot harder, and that helps. And this is the F amp. Doesn't quite drive it as hard, but it has a similar sort of improvement on the signal shape, gets rid of the spikes and gets rid of the foot off the signal as well. So they do make a difference even when you're putting them at the beginning of the wire. Here is a slightly different test. So here I've taken the power wire. I've got a test point. The blue test point is before it goes into the null buffer, and the yellow test point is after the null buffer. So you can see how it cleans the signal up. And so you can see that it detects it early, it squares it right up, and it drops away pretty immediately as well. Now, these are 2 volts per division. So 3.7 volts in theory, to be honest, the 3.7 volts may not have even occurred until here. It may have occurred as early as here, but the F amp has triggered much earlier on it. And it's also dropping pretty immediately that it starts to fall here. It's squaring it right back up again. So you do get quite a clean signal out of an F amp when you put it into the wire, even after the signal's been quite degraded. Okay. DMX. So I wanted to show people the differences. Why? Because DMX is actually able to be driven almost 300 feet or just over 100 meters. So it's pretty good. And the reason that happens is because it's actually a differential signal. And a differential, what does a differential signal mean? Well, a differential signal means that there's actually 2 signals. There's a positive plus signal and a negative signal, and they actually move in different directions relative to the ground wire. And so when this wire goes high, this wire goes low. When this one goes high, this one goes low. And it's actually the difference between the 2 that is being read at the far end. The other thing is if there's interference in the wire, the interference tends to impact both signals, but in the same way. And so consequently, the difference remains somewhat constant. So even though there's a lot of ripple that's going on here, the ripple tends to be reflected on the other end. And so the difference between the 2 signals does not change, despite the fact that there's interference that's been introduced into the circuit, right? That makes a big difference to the ability for the device at the other end to receive this signal. Now, the spikes that you're seeing here, and there's a lot of spikes in this signal, is because this is an unterminated DMX. DMX actually requires that the last device on the chain should have a 120 ohm terminating resistor between the 2 signals. And when you introduce that 120 ohm terminating resistor, you'll notice that the interference doesn't go away, but all of these signal spikes and the reflections that might result from that do disappear, and you do end up with a much cleaner signal. And so that's why you should terminate your differential signals. Even if you're just running a single device, make sure you terminate them. Interestingly, the Falcon differential signals are not quite the same. Because they're only 2-wire differential, whereas DMX is 3-wire, you have a data plus, minus, and ground. The Falcon signal is actually only a 2-wire differential. And so while it does drive them differentially, you don't get quite the same spread. And you have the similar problem with the terminating resistor. So if you're using the smart remotes, setting those termination switches appropriately on the last smart remote in the chain is really important if you don't want to have signaling reflection issues, which you can see up here, and get yourself a much cleaner signal. And you don't want to be terminating it early because that'll screw you up even more. So the next thing I wanted to do was to test all the controllers that I have and look at how they drive pixels. So I tested the F16 V3. I have one of the cult boards here. This is from about a year ago that Dan gave me. I have an older SAN devices here, and I have a bunch of Pixlights as well. And so I wanted to look at what the signals look like when they come out of each of the controllers, and are there any differences? Yes, it is a ton of controllers. This is my test board. This sits in a spare room, and I just connect to it when I'm testing controller uploads and the like. None of these things actually drive pixels in my show. So here they are. And they're very different, very different. And they produce slightly different results as well. So this is 12 volts over the power lead. The Pixlight was by far the best. The SAN devices was also pretty good. You look at the Pixlight signal, and it's actually pretty amazing how good that signal is. The SAN devices drove the pixels pretty well, but the signal shape's a bit disturbed. There's a bit of flickering on the F16, and the signal shape is even more disturbed. And the cult controller would not drive the pixels at all. But can anyone tell me why?
The resistor network.
It's the resistor network. So I went and inspected the resistor networks on these things. The Pixlight is actually got a 33 ohm surface mounted resistor on each of the outputs. The SAN devices, it has a plug-in resistor network. I can't remember what its value was. The Falcon runs 100 ohms, hence the shapes here. It was difficult to measure the culp, but I suspect he's running a kilo ohm based on my attempts to measure it in circuit. And maybe it's not a kilo ohm, but I definitely suspect he's got a higher resistor here, and consequently, he's not able to drive things. Now, obviously, if you threw an F amp on the output, that would be fine. It would clean up immediately and you'd be fine. But yeah, I do suspect, and again, he may have changed this over time, but this generation of boards does not have great driving distance at 12 volts because of that resistor output. His resistor outputs are, again, surface mounted, so you can't swap them out. Dave's, you can swap them out. The SAN devices, you can swap them out. The Pixlight, you can't, but you also don't need to.
Did you do that? Did you analyze that with the one that you swapped to the 30 or the 50 ohm, or is that just still the 100s?
This is the 100. I did do the analysis with the 30 ohm, but you saw that on the earlier slide where I tried it at a whole bunch of different values. And you could see that at 30 ohms, the Falcon was fine. It cleaned it up significantly. I can go back to that slide if you want me to.
No. So it gets closer to the SAN devices or the Pixlight.
Yeah. I'll go. Let me go back to it. If I can find it. Was it this before this one or after this one?
I think it was a while ago. You don't.
It was
you
definitely
do
after
it later.
this. Oh, it's okay. We got plenty of time. I think they gave me an hour and a half, which is heaps of time. There it is. So yeah, so at 30 ohm, a much cleaner signal. None of the reflections at the 100 ohm here. So much better.
Are these resistors just relevant to the controller itself, or do they have any impact on like the differential receivers?
No, they do not work. The differential receivers do not go through these resistor networks. You'll find on the Falcon boards, you'll find these things hidden just in behind the top row of greenies. They're black. They just pull out with a pair of pliers, although be careful you don't damage them. They are they're effectively four resistors, right? So these first two pins, there's a resistor across it. There's a resistor across these two pins, a resistor across these two, and so forth. So yeah, they're just a simple resistor network, and you can try it, right? You can pop one out, and all I did was pop one out and then plug the resistor directly into the socket across the two things to do these samples. I didn't buy resistor networks of all these different values. I didn't need to.
Is it a dip or a SIP 8x1?
Sorry?
A SIP would have 9 legs. I didn't count them.
Yeah, these
this
have
has
eight.
got
These
9
these
legs.
are
I
four
think
resistor packs in a straight
I was
line.
just counting. It looks like it has 9 legs, which could
Yeah,
be-
but this is not a photo of the one. This is one I just
Oh,
stole out of Google.
I'm sorry.
Hey,
That was
these
the
SIPs have
question.
these SIPs have 8 in them. I bought 100 of them, and I tried one in a Falcon F-16, and it works brilliant. They have 8 pins.
Yeah, they do have 8 pins. All right, where were we? We did DMX. We did this.
Sorry if this is a dumb question, but if 30 ohms works better in a Falcon, why does it come with 100 ohm?
It's a good question. I think Dave was trying to be conservative and worried that someone might accidentally connect the power to the data wire, and having an additional resistor in there would provide some additional protection for the board. But it does degrade the signal properties, as you see.
It's to accommodate multiple protocols.
Exactly.
Yeah, maybe. Look, at the end of the day, it's not the protocol. It's actually the design of the pixel. But the pixel's got a 33 ohm resistor on the input, and you're trying to match to it. I don't know. Obviously, Avitech has decided that 33 ohms the way to go, and they support, basically as many different types of pixels as Dave supports. Okay, so I think this is my last slide, or my second last slide. I did. There was a couple other things that I was thinking through and or testing for, and didn't necessarily generate anything useful, but I thought I'd talk about it. What about how do connectors and the like play in this story? And I think the answer there is that if you've got connectors which are corroding is going to add additional resistance into the wire, and so that could cause additional flickering or change how quickly things flicker, or how far you can drive before things flicker. So keeping your electrical connections good, in good condition, could make a difference. So you may not get as much difference if you're not using waterproof connectors, or even your waterproof connectors have been subject to corrosion. I have also read a whole bunch of people having issues with garage remote controls. And so I did a bunch of testing. I put some pixels together, and I put a software-defined radio on my computer and started to scan frequencies which are commonly used for garage remotes and look for interference. Admittedly, I was only running a few pixels, which means I didn't have the whole house is covered in pixels radio interference. I was not able to see from the test I was doing any significant signal interference. Obviously, that doesn't mean that it doesn't happen. It just means I couldn't see it. Given that these things operate at very high frequencies, and this is a relatively low frequency, I guess I was expecting to see frequencies in that 800 to 240 kilohertz range, but there was nothing there at all. So I don't know. Does adding a ferrite core to the pixel wire, because that's commonly, people will say, well, people add a ferrite core onto their signaling wires, etc. The answer to that's no. Ferrite cores are great at filtering out high frequencies, but they don't actually do that. We're fairly low frequencies. They generally won't harm the signal, but it's odds are they won't make any difference and won't help things. So final suggestions, right? You know, if you're running 5-volt power inject, because you're going to need to, that'll get you well. If you're running 12 volts, if you really want to try adding an extra ground wire, that may well help. That may well help as long as you've at least got 9 volts on the power rail. Null buffers will definitely get you more distance, but so potentially would changing the resistor network on your controller. And if you're using 12 volt, use 12 volt regulated and add F amps, I think that's probably going to give you the best of all possible outcomes when you're driving your signals. Any final questions? I think I'm done. I think that's it.
So Keith, on your testing, I know you did a lot of tests around the wire gauges for positive and negative. Did you also do those same tests on the size of the wire related to the data wire? Because I've heard a lot of comments that smaller data wires are better.
Well, so I was definitely running different sides. So, you know, if you remember from the data wire, when I was running a mains cable, you know, I was running the data over what's typically the ground wire on that mains cable. I had no significant issues.
Okay, that was the root of my question.
Yeah, look, there's very little current draw that goes through that cable. So yeah, I was running it over this here, right? This is stranded copper wire, 17 AWG. It ran fine. I definitely wouldn't run 2 separate wires. So in the case of, oh, where'd it go? What am I doing? I'm going the wrong way. In the case of something like this, where I ran, let's say I ran the ground over the 2 whites, I wouldn't run the data over 2 whites. I definitely wouldn't do that because slight variations might cause issues. But all in the same wire, yeah, I haven't seen any problems.
Hell of a job as always, Keith.
It's a slightly different presentation than I normally do.
Well, it's amazing what happens when you invite an engineer to the party. This is great stuff. It's always nice to know the why, right?
Well, yeah, and it'll cause, hopefully it'll help you think a little bit differently when you start to see flickering than you may have in the past, and think about, well, why might that be happening? And maybe you'll be able to apply the right fix the first time rather than the second or third time.
All right. Versus trial and error, you can actually have a systematic approach.
Well, it's amazing how just simply changing those resistors makes a big difference. I've done some tests ever since I watched this video, and it's just too easy. It's pretty brilliant.
I've seen people swap out the resistors before. I just had never actually understood why it helped, and now it makes sense.
And where do you get the resistors?
Someone posted a link in the chat.
Okay.
You could pick them up from Mauser. Pretty much
Yeah.
any of the online electrical wholesalers will sell you resistors.
Yeah, I got 100 for like $12. I'll send a link when I get home if nobody has it, but it's they're real cheap.
And you said they're not on the F48 differential controllers?
No, there are none of these on the F48 because the F48 uses that differential signal. It doesn't send the 2811 signal directly.
So that would be on the differential receivers is what you're saying.
That's right. They would be on the differential receivers. And I must admit, I haven't looked.
Yeah, you know, there aren't any on the differentials. I looked, Keith, I was going to change them all out, but the receiver boards don't have any resistors on them.
I imagine they do, but they're probably surface mount,
Yes,
and they may well be 33. Dave may have changed.
The ones on the receiver are 120 to match the 485 coming out of it. 120.
Yeah, but that's the reception of the 485. It's more interesting. What are the resistors going into the data pins on the greenies?
Right.
Yeah, and don't forget there's a bunch of generic receivers as well that are not Dave's.
So if you're not having problems with flickering, don't pull out and replace the resistor networks. They're fine. There's nothing wrong with them, right? It's just if you need that extra distance and you don't want to be buying, several $5 null buffers, and you just like to increase the distance driven from the controller, then you might want to consider it. And you don't even need to replace all of them. You can just replace one or two of them. You only need to replace the ones that you need.
Yeah, I definitely have this issue when running floodlights because the lights are spread out further away to cover the house.
Right. And they're probably also drawing a lot more current because they're floodlights and they tend to be higher power devices, right? And so your grounds are probably coming up a lot more.
Now, there was a case of flickering I was suffering with for a while, and I was using the pre-made T's, and it was a 3-core T. And what I wasn't doing is I wasn't pulling the data pin out of the place where the power was coming in at the base of the T. And because that data was connected, it was picking up a lot of noise, just like an antenna. Right. And once, pulled that pin, that flickering went away. And that one took me forever to figure out.
Unterminated wires are a real problem because unterminated wires, the signal reflects on it, and that will generate noise into the data signal.
Yep.
So how does power injection affect this with several injection points?
So power injection doesn't change the data signal. The power injection can lower the ground though. And so it can, if I can find it again. It's a problem with bloody slide builds. There it is. When you do power injection, what you're doing is you're dragging the blue line up and probably the orange line down. You're not changing the yellow line at all. Okay. But by dragging the orange line down, you're increasing the difference between the yellow and the orange line. And so you may improve your signaling. Dragging the blue line up is not going to make any difference at all, to be honest. I mean, it's going to help you get more length and more run out of your pixels, but it's not going to do anything to your signaling. This is already heaps of power for your pixel.
So when the F amp first came out, there was a big argument about whether you should actually put in the F amp coming right out of the controller or shortly thereafter. And it looked like, according to your slides, you were proving that as far as a signal quality is concerned, yes, or if you're having signal issues, that F amp coming right out of the board, because everybody's like, no, you don't need the F amp coming right off the board because it's already got all that,
yeah, that's
equalized,
exactly right. Hypothetically, that's exactly right. Hypothetically, you would not put a null buffer immediately after your controller. You would put it either at the end of your wire or halfway along your wire would be the most logical place to put it. The only reason it makes a difference directly off the controller is because it has electrical properties that are better matched to the pixel at the other end than the controller actually does. So you either change the controller to match electrically the properties of the remote device, or you put the F amp in.
Okay, thanks. And your lack of dedication to this the light project is very disconcerting. So maybe next year you'll try and make a bigger effort.
Yeah, I'll try.
Yeah, step it up next year.
Mr. Keith, thank you very much.
What do they say in down under? Good on you.
Yep. I think it's raffle time.
I think it is.
Thanks, Keith.
Yes, thanks, Keith.